Alright, so now go over the problems for levels 3 and 4. Okay, okay, yeah. So I think you can see it. So first of all, level 3. So you're flipping a fair coin, and so you want to find the expected number of flips until the previous 2012 flips are HT in alternating order, sorry. And so you can let S be let S be the string of the coin flips that you want. So, which is to say HT, so on. Okay, and so now we can define two functions, f of n and g of n. And so for f of n, we let it be the number of binary strings of length n without s, or basically such that there's no s does not have any appearances defined. And then now the other function g of n, we let it be almost the same of length n, but now it's with s with the additional constraints that any string that is counted but for any string that is counted, also the n-1 version, basically if we take out the last letter, then s then the n-1 letter string that you get when you take out the last letter does not have contain s. In other words, basically it appears s appears where the g of n is counting the number of strings such that s appears for the first time at the nth flip. So yeah. So now we can find a way to relate f of n and g of n. So in order to be able to relate them, what we do is we can just take a string of length n and then add on s to the end. And so now obviously s will eventually appear, and since s just repeats every two numbers, or sorry, two flips, or alternating flips, that just means that s appears for the first time at either n plus 2 digits, n plus 4 digits, possibly all the way up to n plus 2012 digits. Because remember, there are 2012 flips total in s. And so what that means is that f of n is equal to g of n plus 2 plus g of n plus 4 all the way to g of n plus 2012. And so next, what we can do is let t be the first occurrence of s in the string. And so what we next do is divide both sides by 2 to the power of n in order to turn both sides into a way to find the probability. And so the probability that t is greater than n is simply just 4 times the probability that t is equal to n plus 2 plus 16 times the probability that t is equal to n plus 4 all the way to 2 to the power of 2012 times the probability that t is equal to n plus 2012. Okay, yeah. And so what we can see is that the sum of the p is greater of the probability that t is greater than n in total is simply just 4 plus 16 all the way to plus 2 to the power 2012. So this is just if we use the method of finding the sums of geometric sequences, then this is just equal to 2 to the power of 2014 minus 4 divided by 3. And we can see that actually the probability that t is greater than n is simply just the expected value of t. Well, the total sum of the probabilities that t is greater than n is just this. The expected value of t, which is what we wanted, is just the total sum of the probabilities that t is greater than n. So yeah. So that's the answer to this question. And so now let's move on to level 4. So level 4. Are there integers a and b such that a to the power of 5 times b plus 3 and ab to the power of 5 plus 3 are both perfect cubes? Okay, and so first of all, so I claim that and so to do so, we can see I'll just prove that if a to the 5th times b plus 3 is equal to some perfect cube k cubed, then that implies then that would force ab to the 5th plus 3 to be unable to be a perfect cube. So we will do this through mod 9. And the reason we choose mod 9 is because if x is an integer, the only possibilities for x cubed mod 9 are -1, 0, or 1. And so what that means is that since we're assuming here that a to the 5th b plus 3 is a cube, then that means that a to the 5th b must be congruent to 5, 6, or 7 mod. And so now we can do this case by case. So the first case, if a to the 5th b is congruent to 6 mod. And the reason we choose this first is simply because of the fact that 6 and 9 share a common factor. So a to the power 5 times b is equal to 6 mod 9. So that implies that 3 divides a or b, or possibly both. But we can see that it does 3 obviously cannot divide both, because otherwise this would be divisible by 9. A to the 5th times b will be divisible by 9. And similarly, a also cannot be divisible by 3, because if it were, then 3 to the power 5 would divide this, and so it definitely would not be 0 mod 9. So that means that 3 divides b. And so now you can look at a b to the 5th plus 3. And so a b to the 5th plus 3 mod 9 is simply just congruent to 0 plus 3 mod 9, because as we see, 3 divides b, and there's a b here. So what that means is that this is congruent to 3. And 3 is not a possible residue for a cube, so there's 0 solutions. There's 0, yeah. And so now the next case is if a to the 5th b is congruent to 5 or 7 mod 9. So we'll take these on basically at the same time. So if this is true, then we also know that 3 does not divide a or b, and also a to the 6th, b to the 6th is congruent to 1 mod 9. Because 3 does not divide a or b, and this is just the Euler's totient formula. Because the totient function of 9 is, yeah. And so, sorry, we see that a to the 6, b to the 6 is a to the 5th b times b to the 5th a, or a b to the 5th. It doesn't quite matter, it's the order. And so at this point, we need to split into two cases. So the first case is 5ab to the 5th, and the other case is 7ab to the 5th. And in both cases, they're congruent to 1 mod 9. And so this would just tell us that ab to the 5th is congruent to 2 mod 9, or ab to the 5th is congruent to ab to the 5th is congruent to 4 mod 9. And so we can see that ab to the 5th plus 3 is congruent to 5 or 7 mod 9. But once again, cubes are only positive, negative 1 and 0 mod 9, so neither of these are solutions. And so this means that all cases lead to contradictions. And so it's impossible that, and so this statement is true. And so the answer to our original problem here, which was asking for the existence of A and B, is no. So does anyone have any questions for either of these problems? Okay, well, I guess not. And so if that's true, then so announcement, and then you may leave. So next Friday, the guest speaker will be Justin Lee, and Catherine Lee will continue going over the weekly programming challenge question. Dr. Chong will continue going over the weekly physics challenge problems. And so yeah, and so thank you for coming, everyone, and have a nice weekend. Thank you and bye.